Hello, hello. So right now we're going to take a look at arc length in the rectangular coordinate system. So we have been doing parametric, but we're going back to rectangular coordinates, and we want to look at arc length. So if you have a curve, something say that looks like this, here's your x and y axis, and you have some curve like that, and you want to figure out how long is that curve. What is the distance you would travel if you walked along that curve, starting from point A and going all the way to point B. Now, what you have done before is you've done the distance formula, which means you start at one point and you go straight over to another, kind of like that. And hopefully remember the distance formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. You learned that a long time ago. That is just a form of the Pythagorean theorem when you make this triangle. Your change in your x is your a, your change in y is your b, and your c is the square root of those two added together when you square them. Now, that is great for a linear line, but we have a curve, and so we have to change this a little bit, and it's going to take some calculus. And so I'm going to start rewriting this. Our distance formula, that's what we're going to start with. I'm going to simplify it a little bit. Instead of doing the change in x, x2 minus x1, I'm going to actually just write the change in x squared plus the change in y squared. And then I'm going to do a little fancy algebra here. I'm going to multiply the change in y squared. I'm going to multiply it by the change in x squared over the change in x squared. Now, usually multiplying things is not legal because you're changing things, but of course if I multiply change in x squared over change in x squared, that simply equals 1, and multiplying by 1 doesn't change anything. But it does help us in this case, because I can rewrite this now to look like this. The distance formula is going to equal the square root of change in x squared. And now I'm going to take this bottom change in x squared, I'm going to move it into the denominator of change in y squared. So I'm going to have the change in y squared over the change in x squared times, I still have this change in x squared, so I can't forget about it, there. Okay. Now I see that these have a common change in x squared, and so I'm going to factor those out. So here's my big square root again. I'm going to have a change in x squared, factoring that out. So when I pull the change in x squared out, I have 1 plus delta y squared over delta x squared, which is looking a little nicer now. So let's see here. This allows me to do a couple of things. First, because the change in x squared is multiplying those parentheses, I can actually take the square root of that individually and bring this outside of the square root. So when you take a square root of that square, they disappear, and so you have change in x times what's left over inside the square root, 1 plus delta y squared over delta x squared. But I'm hoping this looks familiar. Delta y over delta x is simply a derivative, and so I'm going to take the square and put it on the outside, and now I've just got delta y over delta x, which is a derivative. I'll write it as delta y over delta x for right now. And I'm going to write in the derivatives the next step. But this is still a distance formula that is between 2 points over here on the side. But we want a curve, we don't want a straight line. So what we have to do is bring those 2 points close together and do many small straight lines. And so we want to shrink this triangle down. We want delta x to get smaller and smaller, and we want to add up all of those lines. So if we're going to add a whole bunch of things up, that means we have to use the summation from 1 to some number n. And we're going to take the limit basically as, you could think of this as n goes to infinity, or you could think of it as delta, the change in x, goes to 0. If your change in x, your a, gets infinitely small, it's going to take an infinite number of lines to cover your arc. Same thing if you have an infinite number of lines, they're infinitely small. You can think of it as both ways. And so I'll rewrite this one more time. We're going to take the summation, I'll write the limit, and I'll do, your book says delta goes to 0, so I'll go delta goes to 0. And I'm going to move the delta x to the back. So of the square root of 1 plus delta y over delta x squared times delta x, because I moved that to the back. Oh wait, sorry about that. I wanted to change something. Erase this. I said I was going to change that into a derivative and I forgot. That is simply the derivative of y with respect to x, or you could think of it as f prime at x. It is the derivative. And hopefully this is starting to look even more familiar. This is the definition, or a definition, of an integral. An integral, you are adding a whole bunch of things up. So we can rewrite this. I'll put it over here to the side. As the integral from some starting point to some end point, from a to b. The s is the same thing as the summation of the square root of 1 plus f prime at x squared, and then every integral ends in dx, which is our delta x over here. Delta x dx. They both stand for the change in x, and that change in x is going to 0. And so that is where the formula for arc length comes from, which is in your book. And so you're basically adding up a whole bunch of small lines, an infinite number of lines, that then will create a curve. I hope that clears a few things up. I wanted to do one more thing with this. One of the examples in your book is a good example, example number 2, but it has a lot of tricky algebra, so I kind of want to go over that to make sure you understand what's happening there. So we'll scroll over to the side here. So example 2 is we are finding the arc length of y equals x to the third over 6 plus 1 over 2x. And they've got a picture of that for you. And we want to find the length over the interval 1/2 to 2. So how big is that curve? And so first thing we do is we got to find the derivative, y prime, because the derivative goes inside our integral. So y prime equals, let's see, x to the third, the 3 multiplies down, so that is going to become 1/2 with the 6, x squared, plus, this you want to think of that as 1/2 x to the negative 1, so I suppose that won't be plus, will it? That will turn into a minus 1/2 x to the negative 2. They have a common 1/2, so pull out the 1/2. I believe your book does that as well. X squared minus, and I'll move the x back into the denominator. So there is our derivative. Now we plug it into this formula here. So we want the integral from 1/2 to 2 of the square root of 1 plus the derivative squared. So now I've got to plug in the derivative, which is 1/2 times x squared minus 1 over x squared. So that there is what will give us the arc length. I'm hoping that much makes sense. In your book it goes on and it solves this integral algebraically. It's a bit of a beast. Try to follow. They skip a lot of the algebraic steps. Hopefully you can follow some of what they do. But I think realistically you need to be able to use this formula, so you want to make sure that you can type this into your calculator somehow. If you want to try to simplify it a little bit, you can, but type that into your calculator and make sure that you can get an answer of 33 over 16, which as a decimal, let me figure that out for you. 33 divided by 16 is 2.063 about. I guess 625. So make sure you can type that in your calculator correctly to get this answer. And I think you've understood arc length enough. Just try not to get lost in the algebra.